Evening, everyone. So when Syed contacted me at the start of the week and asked me if I would be able to step in for a colleague who's unfortunately he was going to give the talk and he's been called overseas, I said, okay, well, tell me about the audience. And he said, well, it's this group of people who are really interested in artificial intelligence and stuff. And we talked a bit about what maybe I could talk about. Because Accenture does various things in machine learning and AI, like robo-advice and things like that. But what I thought you might be more interested in, if you're interested in artificial intelligence, is you might be interested in real intelligence. So what I've decided to do is share with you one man's view of how cognitive processes in the brain actually work. It's got an interesting implication for machine intelligence, and it's also got quite an interesting implication for all of us. So I'm just going to go through a few things here. So title slide. I don't normally spend long on a title slide, but this one's a bit special. You'll notice that this is not me, right? This is describing someone else. My name is not Robert Heck Nielsen. This is the guy who's discovered this theory. I'm sadly not a professor at University of California in San Diego, much as I'd like to be. Confabulation theory. So confabulation, for those of you who may not be totally familiar with it, it's a psychiatric condition that describes the behavior of certain patients who have lesions in one or more parts of the brain that results in them speaking very plausibly, eloquently, confidently about things they've done or seen or claim to know, which have no basis at all in fact. They're not lying, they believe they're telling the truth, okay? But you can tell, because maybe they're an inpatient, but they're just described what they did last weekend, which involved playing golf or something. You can tell it can't be true, but they think it is. So that's confabulation. The reason why it's called confabulation theory will become clear. And the last thing on here I just want to draw attention to is the date. Not only is it not Thursday the 10th of August today, it's also not 2006. So I first came across this about 10 years ago when it was fresh, and it's made such an impression on me. 10 years may feel like a long time, right, in this fast-moving world in which we live. Let me tell you that in the high inertia world of academia, that's the blink of an eye. Right? They've not woken up to this yet, most of them. Right. So with those things in mind, this is the brain, human brain. Although this actually applies to the brain of any vertebrate. And this slightly shaded region here is where the thalamus and the cerebral cortex are sort of close together. And the assertion here is that the thalamus and the cortex together implement cognition. Okay, so here's a slightly stylized version of that. And what this is saying is that there are regions within the cortex and the thalamus that are uniquely paired. And each pairing, which is in this theory termed a module, corresponds to a property of a real-world object. Touch, taste, smell, sound, texture, weight, value, all of these kind of properties that objects may have. And there are about 4,000 of these modules. Each of them's probably got, I don't know, millions of neurons. So, they're quite complex things. And the surface area of each, if you're interested, is about 45 square millimeters on the surface of the cortex. Within each module, there are a large number of symbols, and these are variations on the property, values of the property, if you like. So if it's a color, then you've got red, green, blue, yellow. If it's a texture, it's rough and smooth and slimy and that kind of thing. So each module is a property, and each symbol is a value of the property. And knowledge is encoded through pairwise connections between symbols. Okay? So as you experience the world, sensory input, whether it's visual, auditory, kinesthetic, olfactory, whatever, any kind of sensory input gets passed through this region of the brain and forms connections, pairwise connections between symbols that represent values of properties of real-world objects. So this is how knowledge is encoded in the brain. Let me give you an example. I want you to imagine a red apple. Okay? There's a symbol for the word apple. There's a symbol for the color red. There is a connection in our brains between those two symbols that is excited when we think of a red apple. It was created by us observing a number of red apples. Is this okay so far? Okay. Now I want you to imagine biting into a red apple. A lot more sensory input now. And we have the skin texture of the apple. We have the chewing behavior, which is a motor sensation. We have the color, of course, and we have the taste and smell. All of these pairwise connections is how our experience of an apple is encoded. And our mental world apple object is this collection of connections. This is all according to the theory. Okay? And there are billions of items of knowledge encoded in our brains in this way. Okay, now we get on to the cognition part. Now, Heck-Nielsen's theory is that cognitive processes are controlled in the same way that our motor movements are controlled. Okay, now you often hear people say quite blithely, the brain is a muscle. What they don't know is how close they are to the truth. He describes thought, cognitive processes, as a phylogenetic outgrowth of movement. The mechanisms that surround this part of the brain that tell it what to do are identical to the mechanisms that control our muscle movements. Biologically, absolutely the same. So when these thought command signals that make this part of the brain do cognitive things are created in the same way as muscle movements. Now, a single muscle contraction, if you play a key on the piano or something, doesn't do very much. You maybe play a note. Not very interesting. If you can string a few together, you can play a scale. And if you can learn some very complex movements, then you can learn how to play a Beethoven sonata or something. In the same way, with cognitive processes, a single contraction, single thought command input, does something fairly basic. But you can learn, and we've all learned, many different sequences of contracting these modules that perform very complex, high-order brain functions. Like, I don't know, multiplying two numbers in your head. That requires a lot of practice and certain sequences of contractions here. So what this is saying is that you get a single thought command signal which causes all of the symbols in a module to behave in a certain way. I'm not going to go into the details. We've only got a few minutes. After about 40 milliseconds, that's kind of happened, and then the next phase begins, and it continues until a conclusion is reached. And of course, being the brain, this is massively parallel and massively interacting. Yeah, so these modules are sparking off similar things in other modules until something intelligent happens, maybe, or not. And then when if one of these confabulations, one of these sequences of modular contractions, if you like, yields in a useful conclusion, then something may happen. So this could be it could be a motor movement, or it could be another thought, or it could be I don't know. Basically, any aspect of behavior, an emotion could be triggered, right? This is the first theory, to my knowledge, that's ever come up with an origin for behavior. Previous researchers haven't been able to do that. Right, bit of maths now. And this is where the quite profound implication for machine learning comes in. The vast majority of machine learning is based, in one way or another, on Bayesian mathematics. Now, Bayes' theorem is to do with, if you know something, then the probability of something else, is related to that knowledge. Okay, at a high level. So in this example, we've got 4 assumed facts: alpha, beta, gamma, and delta, and we've got a possible candidate conclusion from those facts, epsilon. In Bayesian mathematics, and in neural nets, therefore, what the machine is trying to do is find the epsilon which has the greatest probability of being true given these assumed facts. Okay? Now, there's nothing irrational about this. It works. It does a lot of good things, and machine learning is showing that can actually be quite useful. What's odd about this is that that's not what's happening in the brain. There is no neuroanatomical structure that implements Bayesian mathematics. The brain does not work that way. And what Heck-Nielsen says is happening is something called maximization of cogency. And this is how it works. He says that the wiring in the brain is able to maximize the probability of the assumed facts being true given the conclusion. So Bayesian, maximizing the probability of the conclusion being true given the assumed facts. Cogency, it's the other way around, maximize the probability of the assumed facts being true for a given conclusion. What this is saying is that in the case where there's just a binary, a yes-no answer, a Boolean logic type operation, then it gives the same result. But when it's a bit more complex, a bit more fuzzy, it gives a very different result from the Bayesian alternative. This is quite profound, I think, for machine learning, because it means that no matter how good our neural nets get, if the underlying mathematics isn't the same as what we do, then the behavior of the machine will never be the same as what we would do. Doesn't mean it's not useful, the way it's being done at the moment, but it means that it won't ever be quite like us. Perhaps, I'm speculating here a bit, perhaps innovation comes as a result of doing it this way rather than the Bayesian way. To find out whether this theory had any value, could do anything similar to what we do, what Heck-Nielsen then did was he built a computer simulation of it, and he fed into it millions of news articles. I'm going to skip over a little bit here because a little bit short of time. He fed into it millions of news articles, which caused lots of those pairwise associations to be created between pairs of words. Okay? And then he took it out of learning mode and put it into production mode. And what he did was he fed in a sentence, which you could have taken from the first paragraph of another news article that it hadn't ever seen. So this is all new data. Then he gave it 3 words of the next sentence and said, please complete this sentence or generate some more words after this. So this is the context. This is the start of the next sentence. And then the red, the next words, is what the simulation produced. And I've got some more examples of that. So again, the top one here, this one is actually without context. So if he just said the New York and then said, give me some words, then it said New York Times computer model collapses. But if you gave it the context, then it came out with something contextually relevant, and so on through. Downtown events were interfering with local traffic, the New York city centre area, and so on. You can read through all these yourself. In other words, the words that were generated could have been the next sentence in that newspaper article. They weren't, though. They were confabulations. Okay? They were plausible. They could have been that. If you didn't know they were wrong, they could have been that. This is where the name confabulation theory is coming from. Here's some more. Okay, enough of those. Right. So, characteristics of this theory. Unlike machine learning, deep learning, all of this stuff, in confabulation architectures, there are no algorithms. The only software is the implementation of the ability to create these pairwise connections and the ability to confabulate then, to use those to generate sentences. There's no preset rules, ontologies, priors, or Bayesian networks. So the conclusion that he reaches, and which I broadly share, based on this being true, is that thinking is pretty strange. Specifically, we all confabulate all of the time and get away with it. Thank you.
I've got a quick question before we ask you Rick's.
Sure.
Why don't you tell us a bit about yourself? So you told me you're the most interesting person who works at Accenture.
Okay, you've set the bar quite high there. Where is he? Yeah, so I'm Peter McElwain-John. I joined Accenture last year after a fairly long career in IT. I guess I've been in technology quite a long time. I had my first home computer when I was 9. It was vast. It was an old accounting machine, more electromechanical than electronic. Took up half the garage. Earned my first money from software when I was 14. Did a degree in mechanical engineering at Imperial College. Earned a DTI Innovation Award for the... Actually, there's a shoe connection here. I didn't think of that. I did the prototype for the Clark's solid-state foot gauge. So, you know, the sort of floor tile that you stand on, and it tells you your foot size. And I've done loads of things. I've worked for Microsoft, Wipro, banks, yeah, lots of stuff. Always interested in all sorts of technology. I have never been as excited about technology as I am today. The pace of change is unbelievable. AI, after 50 years of flatlining, just delivering nothing of any value, any practical value at all, is suddenly going to change our lives, and I can't wait to see it happen. Yes, I'm a bit scared about it, to someone else's point, but I'm more excited than scared.
Cool, thank you. Any questions?
So I guess you've got this confabulation theory and you've got the Bayesian networks, and they seem to be two like antagonistic kind of theorems about how machine learning should improve. Are you saying so that the billion years of evolution that's led to our human thought, is that kind of like the rule of thumb in which we should be aiming for, or should we be aiming for better than that?
Oh, better than human. Well, I think that's quite hard. So there are specific things that we do where machines can be much better than us. But when you get into general things like general intelligence, I don't know what better than human would be. I mean,
could we even envision that, given that we are only human?
No, I think something better than human will be designed by the things that we build.
Okay.
Yeah, I think that's the most likely outcome. What's odd? Well, what's potentially not odd is that there are, to my knowledge, no commercial implementations of this. There are very few even references to it in academic literature. But at the same time, there are no refutations of it either. When I read it 10 years ago, I thought, if this is right, then the American Department of Defense will jump on it and kill it. Or rather, will take it for their own use. Maybe that's what's happened. You're shaking your head. You're skeptical.
Because consciousness research nowadays says something similar.
Consciousness research.
Yeah. So what you're talking about is one point of consciousness where, so that's one of the areas in psychology where those are so big. And current consciousness theory says that it's in the interaction between the brain regions. So when I'm telling you stuff, those are stimuli, as you said, those are different regions of your brain is starting to communicate with each other, and consciousness lives within that, but no one can prove that I don't know what I'm telling you.
Right. Actually, this theory says nothing about consciousness.
Okay.
No, this is about cognition.
Yeah,
Which is different. Like you say, consciousness is, maybe it's an emergent property of all of this, but
cognition consciousness is just a more narrow framework. So everything is cognitive, and whatever you do just gets more narrow and narrow. You touched on volition and consciousness in your speech. Volition was when you talked about how fast the brain actually reacts. So the 40 milliseconds, 80 milliseconds, these sort of things. So a psychological thing now, if I throw you a ball, you catch it. Your brain is constantly predicting the future, so everything that you say you do is in the future, and your brain is just generating all these sort of answers that can be your query, because actually for your brain to react to catching a ball, based on fMRI studies, is a lot slower than you could actually do. So they still have no idea how.
we live in the past, right? We live in a constant state of what just happened. Certainly the conscious brain is about half a second behind the physical brain. Because it's a fixed.
Planning? What about planning? We do look ahead, so we don't live solely in the past.
Oh, absolutely, but it's
reaction is based
so the
on
brain does the planning, and then our consciousness tracks that about half a second behind.
Let's bring that conversation offline.
Yeah.
Just time for two questions quickly. So maybe the gentleman here.
I'm just curious about, you mentioned that the confabulation is not a paradigm that's available in machine learning, but there is a system in machine learning called latent variables, where you try and explain the data, rather in almost similar terms, you create stories that explain the data, which is precisely what you're trying to do here, is it not?
I'm not familiar with that. Maybe we can talk about that after. Yeah. Okay.
So, I mean, a lot of your speech recognition, for example, or predictive text that works on, some of them work on neural networks, but some of them work on something called hidden Markov models, which are essentially latent variable models, which have learned, in order to learn to create stories based on the data that is in front of it. So, essentially, that boils down to confabulation.
It sounds like it's got some similar properties. Whether it can also be turned into this productive mode of operation.
If you use Google predictive text, you're pretty much doing that. So, essentially what you showed about the New York Times predictive text is very
There
similar
are
to what
similarities. Yeah.